Okay, so this is part two of chapter 12, Energy, the Great Transition. And this is the part where we're going to go over the things that we're starting to transition towards, renewable energies. Right? So, basically going to go over some of the technical basics of each. Actually, before I do that, let me kind of shift back for a second to the energy statistics I started part one with, to highlight how much of each of these things we're going to go over, representative of the total energy mix, right, in the United States at least, pretty similarly throughout the world right now. So renewables, the stuff we're going over now, basically represents 11% of the total. I'm going to specifically go over wind, which is 21% of renewables, but 2.3% of the total. Solar, only 6% of renewables, and less than 1%, right? 2/3 of a percent of 1% of the total energy usage in the United States. But both of those are growing faster than any of the other sources of energy. And we'll talk a bit about bio waste and biofuels. I'm not really going to talk about wood. That's pretty self-explanatory, burning wood. Geothermal and hydroelectric. Okay. So let's go back. Okay, so starting with wind. Right, so you've likely all seen, either live or at least on TV, wind turbines. So been around for a long time to grind grain and stuff, but the modern windmills are basically producing electricity. What's interesting about no matter besides solar panels, right, or geothermal, which we'll talk about in a second, basically all of the other types of things that produce electricity, which is what most renewables are for, including all of effectively wind energy, is no matter how technologically advanced it seems like the energy source is, in the end of the day, it's doing something to spin a turbine to produce electricity, right? In the for wind, it's literally taking the motion energy, right, of the wind turbines and harvesting that to literally then turn the generator turbines, which then produces electricity in a process that your science teachers would be better able to well explain to you much better than I would. Okay. So again, wind almost exclusively for electricity production, other than like very, very old wind turbines, right, to like grind grain and stuff like that. Solar energy. Now I mentioned in the part one that almost all renewables are effectively some form of solar energy, including the fossil fuels being old stored solar energy. Even wind is solar energy, right? It's the different temperatures of the air, the variations causing kind of the wind to flow, right? So again, that's all heated from the sun as well. But what we normally think of as solar, right, is literally the thing of using the sun to produce electricity. And what most of us think of as the solar panels, right, is more technically called solar photovoltaic. Right? So this is the one form of energy that directly converts the sunlight into electricity through the silicon, and again, process that your science or engineering, actually in this case, likely instructor would be better able to describe the details than I would. Right? But so solar panels, so solar photovoltaic. There's also solar thermal energy, right, which is basically doing the same thing as I mentioned a second ago. Like the wind turbines are using the motion of the wind to turn the turbines. Even when electricity is produced from coal or natural gas or even nuclear, for those processes, it's basically to heat water that then is used, that heated water, the steam, to spin a turbine to produce electricity. So solar, although some of it's directly used through the solar panels to produce electricity, solar can also be used to do the same thing as those fossil fuels and nuclear, right? Concentrating the sun's heat to boil water, and using the steam to rotate a generator to produce electricity, or to use the hot water to actually heat areas. So it's like one form of renewables that is not for electricity production, it's literally for heating. And there's other form of solar energy that can be used both for heating, is in building designs, right? Heating and cooling, actually. So this is basically, it's called passive solar. So designing and situating buildings with materials and in facing various directions in such a way such that it the walls and everything store and use the energy, the sun's energy in the winter to heat, reject the heat in the summer to cool. So passive solar, right, the growing area in building design. However, this is typically not included in any kind of energy statistics effectively directly. If anything, it is actually just reducing the amount of primary energies we need to produce as far as the amount of electricity and other things. So it's in a way more like energy demand reduction in terms of produced energies for the passive solar. So if you look at solar growth, right, in the United States, you can see that it's split between the distributed, which is what you would normally think of, right, people on people's homes, right, the solar panels, versus utility scale, which would include both solar panels in effectively solar farms, in addition to kind of the concentrating, right, power, right, of the sun's heat for the solar thermal. What's interesting is, although we think of the solar panels first, that's actually a smaller fraction, right, of the total than the utility scale, both solar thermal and solar farms. You'll notice that it oscillates. Again, this is the United States production, so it oscillates throughout the year. And hopefully you can logically think what that would be is the low points are the winter when there's less sunlight, and the high points are the summer when there's more sunlight. Now, besides, well, that actually starts to highlight one of the challenges that solar and wind have had in becoming a more and more significant portion of the energy mix, especially the electricity production mix, is that they're intermittent. So what does that mean, they're intermittent? Well, obviously the wind doesn't blow all the time, the sun doesn't shine all the time, such that they can't produce energy all of the time, right? So, absent an efficient way to store the electricity that they do produce when the wind is blowing and the sun is shining, they have a technical limit, right, which changes as technology improves, but the technical limit of what percentage they can represent of the total mix of energies that produce our electricity, right? So they can't represent all of the electricity in the grid, because they need to. The electric grid's a kind of an amazing thing. Basically, the amount that's put into it needs to be in basic constant balance with the amount of energy being used. And when you can't depend upon these as a flow, being able to modulate it like you want because they're intermittent, it causes technological constraints. Now, having said that, electricity storage technology is improving quickly. Obviously, we have batteries, so we've had electricity storage forever, but not an efficient way. A lot of loss in those historic batteries that we use to power our flashlights and things. But and obviously needed on much higher scale when you're talking about the crazy amounts of electricity that are needed to power a city, for example, or the United States. So need much higher scale. Well, all of that is improving. Here's one article kind of talking about that. And as this improves, the ability to store, well, the challenge from intermittence of solar and wind becomes less of a constraint. So traditional hydroelectric, or traditional hydropower. You've all likely seen a dam, maybe you've even driven by or gone on a tour of the Hoover Dam out in Nevada. But again, it's this using a different, right? Using the potential energy, actually positional energy for a traditional hydroelectric plant of the water being higher, right? And being able to use the force of the water coming down to spin the turbine to produce the electricity, right? And then take it away on the electric grid, right? To where it's needed through the transmission lines. There's other types of hydro, right? There's also hydro that you can use, that's being used in rivers, which use the same kind of flow of water rather than, well, it's still the positional energy because the water only flows down, obviously. But then there's also tidal hydro. That is an emerging technology to actually use the tides in the oceans and that motion to spin the turbines. Not a lot of that in the energy statistics, right? But it's a potential area of growth for hydro. Whereas at least in the United States, most places that are good for having hydroelectric dams are being utilized, right? So not a lot of growth in this portion of electricity generation or renewable power in the U.S. anyway, or in most developed countries, but in a lot of developing countries, right? China's expanding their hydro capabilities, as are other developing countries. Okay, off to biomass. Right? So what is biomass? Well, basically it is recent stored solar energy from photosynthesis from recently deceased plants and animals. Right? So wood is effectively not effectively, wood is biomass. Right? Crops that are used to produce biofuels, for example, are biomass. All these other agricultural products and some organic, right, garbage, right, can be used for various biomass. And this biomass can produce energy in various ways. So we obviously know about the burning of wood, right? Well, we can also burn, some of these other biomass products, right? Converting to methane gas, right? So you might see, landfill gases, for example. So if you ever go by a landfill that's been, has the garbage buried, you often might see vents coming out of the ground to basically let out the methane. Well, you can actually produce that with these various forms of biomass. So convert the energy within those recently deceased organic materials into methane. So burning, converting to methane gas, and converting to liquid fuels, biofuels. Right? Most in the U.S. being ethanol, predominantly from corn, or biodiesel, with the same basic ideas. So, how does that work? Well, like corn for ethanol, to produce ethanol, you grow the corn crops, you refine it, you separate out the sugars, you dissolve it to make ethanol, you can use it to power your car, releases CO2, but then when you grow more crops, right, the crops absorb the CO2. So what makes this, at least in the use of biofuels, it's close to a carbon neutral process, the usage of them, right, this piece of it, because what the exhaust you use effectively, then if you're growing more, you continuously use that same carbon effectively to produce more biofuels. However, all this production process, right, the actual production of the corn, rather than just the consumption, right, the use of the fuel once it's produced, well, that does produce a lot of greenhouse gases, right? And you have to transport it to grow the corn. And as we talked about in part one, very low energy return on investment. So there's a lot of energy in this process, right, to produce the biofuels required. So, and that energy is not likely to be only renewables, so greenhouse gas is emitted from that. So more on biofuels, right? So besides ethanol, biodiesel, basically from vegetable oil, same basic thing, right? But for vegetable oils, soybeans, food grease. There's actually, I forget the name of the documentary right now, but there was a guy who was driving around who had converted his van to run directly on basically vegetable oil, right? And he'd basically stop at fast food places and say, "Hey, can I get your old grease?" And he could basically run his van. Often these are mixed with petroleum, which is true for ethanol as well, right? So if you go to a gas pump, typically you'll see contains 10% ethanol, right? So 10% of what you're putting in your gas tank is biofuels. And so, the most common mix for diesel, right? For biodiesel is like a 20-80 mix. So there's some advantages over petroleum diesel, right? Is that there's no sulfur, right? So less toxic, right? Less pollutants. In fact, there are other documentaries I've seen where they've made a biofuel from like these vegetable oils and actually were able to consume it, right? Don't try to consume or drink your gasoline or your diesel fuel; you will perish, right? Ethanol, right? Talked already a bit about that. Liquid fuels to replace oil from both corn and sugarcane. As we talked about, sugarcane in part one, sugarcane used a lot more in Brazil. U.S. still predominantly or significantly corn. Right? Sugarcane has a much higher energy return on investment, right? So that is a better form. A growing emerging technology is what would be called cellulosic biomass, where basically you're not using corn or sugarcane, i.e. food products, to produce your biofuels. You're using wood, waste paper, switchgrass, effectively grasses, the stalks of the corn plants, right? So cellulosic has a lot of advantages over these food crop based biofuels, because, well, one, it doesn't take away cropland, right? Like using corn and sugarcane, right? Those are typically things that would otherwise just be discarded and thrown away. So cellulosic is better. Better energy return on investment as well than especially corn. And as just said, doesn't take away cropland. But then there is another way to produce biofuels that is an emerging technology, and one that I'm actually particularly kind of keep an eye on and excited about, is producing it from algae. Right? So I got to give credit to, there was a year in 2000. There have been some years where I have students do a presentation on this. So if you're listening to this, you might be in one of those years. Not here in the spring of 2020 when I'm making it, however, in this coronavirus strange environment. But biodiesel from algae, right? So you basically grow the algae, extract the oils, separate out the oils, and then use it. So a lot of advantages for algae, right? So this chart, for example, shows how much oil, plant oil, which then you can turn into the biofuels, you can get per hectare, which is, I believe, roughly like 2.5 acres of land. Right, so astronomically more than many of these other plants. Right, but just like the other biofuels, no sulfur, isn't toxic, faster growing than most of these other types, than most other things used to make biofuels. So can grow faster than most other food crops. Can be produced with ocean and wastewater rather than having to use fresh water or potable water like you do predominantly growing, food crops. Biodegradable, which is effectively true for the others, biofuels as well. Harmless to the environment if spilled, right? So those are advantages over petroleum-based liquid fuels. Another great advantage, in addition to not having to use fresh water, you also can do it in places where you couldn't grow crops, right? Can grow in deserts, for example, right? Grow in places that are unsuitable for crops, so you don't take away from the ability to grow crops from cropland. So all kinds of crazy advantages to algae. So you would think with all these advantages, grows faster, um, doesn't take away croplands, you get more out of it per unit of land than you do for the other crops. Why isn't it just dominating? Well, um, technically, I guess it's harder to keep the process pure, so scaling it up has some technological advantages that I'm not an expert in to be able to explain. But this is, growing, right? And companies, you'll see commercials these days for companies like ExxonMobil talking about how much biofuels they're making, right? And how much, and specifically even talking about algae. It is an exciting one, right? I think it has a lot of promise for the future. So getting away from the sun-based fuels, we talk about geothermal, which is basically using the heat from the earth to either heat buildings or to, again, spin a turbine to produce electricity. So if you go very deep into the earth, right, obviously further down you go, the hotter it gets. So you can actually produce electricity. So it would be the product called a geothermal power plant. Heat the water, spin the turbine, just like the fossil fuels, just like the concentrating solar panel from the solar thermal, to spin a turbine, produce electricity. Closer to the surface, right? Maybe 70 feet down, you can use the relatively constant temperature of the Earth to both heat and cool buildings, right? On the Dutchess Community College campus, right, the dorms are geothermal. The dorm is geothermal heated and cooled, as is Bound Hall. So that's a kind of a quick overview of geothermal. Many of you might not have heard of geothermal, right? But once this coronavirus pandemic ends, and eventually when oil prices go dramatically higher, which at some point they will, I think geothermal will be something that everyone will be as familiar with as you are now hearing about solar panels at some point. It's something I would love to have in my house, but it's really expensive to put in, right? Nuclear, well, what's it doing here, right? It's not a renewable, right? It should have been in the non-renewable portion. And I could have talked about it there, but I lopped it in here because although it is not renewable in any way, shape, or form, and it has all kinds of challenges as far as nuclear waste, since we just finished talking about climate change, it is greenhouse gas clean, at least, right? So for people who talk about climate change as something we need to focus on, although nuclear has other environmental potential, very significant environmental problems, greenhouse gas emissions is not one of them. So it is definitely talked about as one of the potential mitigation methods for climate change. Basically, it's a process of fission, right? The sun does fusion, which I guess there's experimenting with, but basically producing crazy amounts of heat energy from effectively nuclear reaction. But we do fission where the atoms are split apart, as opposed to the sun where they lop them together, where atoms are like combined. But anyway, fission, split the atoms apart, releases energy, heat. And again, although as technologically advanced of a concept as this is, in the end of the day, it just heats and warms water to spin a turbine. Use the steam to spin a turbine to produce electricity. I'm going to mention fuel cells and hydrogen briefly here, although they are not a source of energy like the other renewables we've been talking about. It's more of a energy carrier, like a way to use energy from the other sources, like electricity, right? Electricity isn't a source of energy. It's produced from the other methods we've just finished talking about, right? Well, that's the same for fuel cells and the hydrogen used to power those fuel cells, right? It's an energy carrier, but it needs to be produced from other primary energy sources like natural gas or wind or solar, etc. But bottom line, it can be used to heat homes or produce electricity for homes, to power cars, heat and water, as far as the usage of it, are the only byproducts. Now, there's going to be greenhouse gases and other stuff if the hydrogen is produced from natural gas. But this is also an emerging quote unquote renewable technology because it's infinite ability to produce hydrogen. So to the extent that we're utilizing renewable primary sources of energy to try to, for example, power cars without electrifying a transportation system, this is just another method to kind of get there. So we talked in a prior chapter about negative externalities of pollution, right? That the use and production and use of many products produces pollution, including, for example, fossil fuels, right? Well, because renewables don't have that same negative externalities in many cases, although they have their own other ones that we could talk about, but aren't going to it at this stage, right? But for clearly less negative externalities, and for climate change, for wind, solar, much less, much better. You can consider them as having positive externalities, right? So the benefits of using them have social benefits. So if you have solar panels on your house, for example, not only are you benefiting directly from the electricity you're producing from those that you don't have to buy from the grid, your use of the solar panels means less electricity has to be produced from coal to power the grid, right? Or other methods like that. So that basically has a benefit beyond. That's why it's an externality. It's a benefit not just to you, but a benefit to society, right? It has a social benefit as opposed to the social cost of the pollution. So when we had negative externalities, right? The idea was, hey, unless you internalize that externality, unless you reflect the cost of those social costs of the negative externalities in the product, too much of it's going to be used. Well, in this case, unless you reflect the benefits of those social benefits, too little of it's going to be used. So conceptually, right, in the chapter for negative externalities, we wanted to shift the supply curve to the left. Right? Well, here we want to incentivize people to use these things because of these social benefits. Now, this isn't obviously a case of using more renewables, right? But another example of positive externalities that makes sense to talk about today in this coronavirus pandemic situation we're in is subsidized or free immunizations, right? Once we get to a point where there is actually a vaccine for the coronavirus, everybody's going to want almost everybody's going to want everybody to get a shot, whether they can pay for it or not, because it has benefits to all, right? There are social benefits. So that's why many vaccines are either subsidized or are given out for free. So in terms of renewable energies, right, that have far less negative externalities, so you can consider that a positive externality, we want to incentivize people using them and producing them. So how do we do that? Well, we can give people a subsidy so they demand more of it, right? Putting solar panels on your house is expensive. Putting in a geothermal system is expensive. But if you give people tax breaks for installing solar panels, for example, that is going to increase how much people do it because part of it gets paid for, right? And here's some examples of some of the tax breaks, right? As I'm giving this lecture in spring of 2020, more or less, I believe the subsidy level, the tax breaks for installing solar panels on your house in New York is about 25%. So basically the government pays for 25% of your solar panels as it exists. In some countries, it's even more lucrative, and it's sometimes in the U.S. it's been, and it might be in the future as well. So in addition to giving people subsidies to demand more, you can reduce the costs of it. So give people, companies, incentive to produce more. So there are production tax credits, right? So for various types of renewables that you produce, companies get paid right, effectively subsidized to produce that electricity, or investment tax credits, predominantly used for things like for wind turbines. So basically, they get paid, get a tax break, right, to basically put in those turbines, right. So it gives them more incentives, lowers effectively the cost of installing them, which gives more incentive to install them. We talked about this actually in a prior chapter, in renewable portfolio standards, right? So law requiring some minimum amount of electricity to be produced from renewables, and many states have such renewable portfolio standards saying, hey, by 2030 we need X percent of our electricity produced from renewables, right? So many states in the U.S. have such standards or targets. There's also renewable fuel standards, right? So try to increase the usage of biofuels. There's a link for that. There was an Energy Policy Act in 2005 that provided guaranteed loans for low interest guaranteed loans for low carbon energy production. Again, giving more incentive, lowering the costs of doing that. The 2009 economic stimulus package, right, for the Great Recession included new tax breaks for solar water heaters, geothermal heat pumps, wind energy systems, extra tax breaks again. The whole point of all of these is, again, because of the positive externality, to incentivize people to use more of it than they would otherwise, right, to help subsidize their implementation. So that's a quick overview, right, of some of the key renewables and some of the ways where the transition is trying to be pushed along faster than it might happen otherwise. So with all that, the International Energy projections in 2017, based on what they think is going to happen with the energy mix. That's not what why isn't it letting me go that side? Energy mix, right? And so from 1990 history, so here we are roughly when they did this estimate, 2015 projection. The good news, right? Renewables, right? So this is in quadrillion BTUs. The exact British thermal units, the exact measure isn't important, but the question is how much is each of these things growing or shrinking? So this is the world, right? Not the U.S. at this point. Good news, right? Renewables growing, roughly doubling is the projection, right? From basically that 25-year period. The maybe not so good news from a climate change perspective is that petroleum also projected based on their estimates to grow. Natural gas also expected to grow. Coal staying about flat. So yes, renewables are growing and they're growing faster than everything else. But as far as the transition, with the other ones growing as well, it's still being forecast at this stage to be a slow transition from fossil fuels to renewables. And as we talked, sorry for the little break there, as we talked about in the climate change chapter, one of the things we went over was a 2018 IPCC report saying, hey, what do we have to do if we want to keep the total warming below an average of 1.5 degrees Celsius? Well, that would require massive reductions in these fossil fuels, right? Getting rid of the majority of them. Whereas these forecasts, or the one that we just looked at, basically, although it has oil growing, right, it's still shrinking as a percentage of the total because renewables are projecting to be growing much more. But if you notice, renewables expecting to grow from 8 to 18% of the total, which is a 41% growth, much less than what's needed. Nuclear, not so bad, but These are not, right, natural gas actually growing as a percentage of the total rather than shrinking, oil shrinking a little rather than a lot, and coal shrinking a decent amount, but much, much less than the almost 100% shrinking that they're saying would be needed to kind of stay under this target of 1.5 degrees warming climate change. And that is the quick discussion of energy, chapter 12.